This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 5 of Week 5, Feedwater Heating and the Regenerative Rankine Cycle. We bleed a little steam out of the turbine to preheat the feedwater, giving up some work to buy a higher cycle efficiency. By the end, you'll write the open feedwater heater energy balance and solve for the bleed fraction from steam table enthalpies. Why regenerate? Cycle efficiency rises when you add heat at a higher average temperature. In a plain Rankine cycle, cold condensate hits the boiler, and a big slug of heat is spent just warming that liquid up to saturation, all of it added at low temperature, which drags the average down. Regeneration fixes it. You bleed a small fraction of steam partway through the turbine and use it to preheat the feedwater. The boiler no longer adds that low temperature heat, so the average heat addition temperature climbs and efficiency climbs. The trade is a little lost turbine work, but the net is a clear gain. The open or direct contact feedwater heater is just a mixing chamber held at the extraction pressure. The bled steam mixes straight into the feedwater, so everything leaves at one state, saturated liquid at the heater pressure. Write a steady flow energy balance. Extraction flow times its enthalpy plus feedwater flow times its enthalpy equals the combined flow times the outlet enthalpy. Put it per unit of total turbine flow and define the bleed fraction Y. The balance collapses to one line, and you solve for Y, outlet minus feedwater enthalpy over extraction minus feedwater enthalpy. One unknown, one equation. The open heater also deaerates the feedwater, which is why it's called the deaerator. The variable table. The bleed fraction Y is the unknown. The three enthalpies are the whole game. Extraction steam, feedwater in, and heater out, all in BTU per pound mass from the saturated pressure steam table. The heater out enthalpy is always saturated liquid at the heater pressure. Pull those three, run one balance, and Y drops out. One caution, every enthalpy must come from the same table family. Don't mix an IP value with an SI value. A closed feedwater heater keeps the streams apart. It's a shell and tube exchanger. The bled steam condenses on the shell while feedwater runs through the tubes, so the two can sit at different pressures and no interstage pump is needed. The condensed extraction, the drain, either cascades back to a lower pressure heater or gets poked forward into the feedwater line. Performance is set by the terminal temperature difference, how close the feedwater comes to the steam saturation temperature. Real plants run several closed heaters plus one open deaerator. An economizer recovers boiler heat from the flue gas instead of from the steam. It's a gas-to-water heat exchanger in the exhaust path that preheats feedwater on its way to the drum, recovering heat that would otherwise go up the stack and lifting boiler efficiency by roughly 5 to 10%. The recovery is a straight heat balance. Gas side equals water side. Don't confuse the two preheaters. The economizer is fed by hot flue gas, combustion waste heat. The regenerative feedwater heater is fed by extracted steam, turbine bleed. Both deliver warmer feedwater. They just tap different waste streams. Worked problem. A regenerative Rankine plant bleeds steam into an open feedwater heater running at 100 psi absolute. From the steam tables, the extraction steam, saturated vapor at 100, is about 1187.5 BTU per pound mass. The feedwater entering from the condensate pump is about 70. The heater outlet, saturated liquid at 100, is about 298.5. Find the bleed fraction Y. The plan, write the open heater balance, solve for Y, plug the three enthalpies, and sanity check. Plug the three enthalpies into the rearranged balance. The numerator is 298.5 minus 70, which is 228.8, the enthalpy the feedwater must gain. The denominator is 1187.5 minus 70, 1117.8, what each unit of bled steam can give up. Divide and Y is about 0.205. So roughly 1 pound in 5 of the turbine steam is bled to the heater, and the rest keeps expanding to the condenser. Real open heater bleed fractions land between 15 and 25%. That bleed fraction is the lever the whole cycle turns on. The bled 20% skips the rest of the turbine, so gross work per pound of boiler steam drops a little. But the boiler now gets feedwater at nearly 300 BTU per pound instead of 70. So boiler heat input per pound falls by about 229. Because heat input falls more than the work does, thermal efficiency rises. That's the entire payoff of regeneration in one fraction. Real plants stack several heaters at staggered pressures to capture that gain again and again. 4 traps. 1. Using the saturated vapor enthalpy for the heater outlet. The open heater discharges saturated liquid, so use HF, not HG, or Y blows up past 1. 2. The wrong enthalpy in the denominator. The driving term is the bled steam's enthalpy drop. Extraction minus feedwater. 3. Confusing the economizer with the regenerative heater. The economizer preheats from flue gas on the boiler side, the regenerative heater from extracted steam on the turbine side. 4. Open versus closed bookkeeping. Open heaters mix to one outlet and need a pump after each. Closed heaters hold a pressure difference and route a drain. Write the balance that matches the heater shown. Bookmark the regeneration pages. Why regenerate? Bleed steam preheats feedwater, raising the average heat addition temperature and the efficiency. The open feedwater heater balance with the outlet that's saturated liquid. The bleed fraction formula. The saturated pressure steam table, where you read HF and HG, and the economizer heat balance for flue gas recovery. The regeneration relations and the steam table together solve every open heater problem. You now own the regenerative move. Bleed a fraction of steam, mix it into the feedwater, and solve one energy balance for that fraction. Today's open heater landed at about 0.205. Next topic, we follow the steam to the cold end of the cycle. The condenser that closes the Rankine loop, and the cooling tower that dumps the heat to the atmosphere. Same enthalpy bookkeeping on the heat rejection side. Bring your steam tables. See you in topic 6.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.